Hello, my name is Cody Seeley, and I will be doing a network analysis and data center firewall security implementation for the company We Are University. Introduction. Basically, my project is a documentation of the university's backbone network location, which is the industrial building, which houses all of the major network devices and WAN links for the university. I'm going to attempt to explain current network operations, both from a physical and logical view. I'm going to be talking about my implementation for the network, which is a data center firewall, and the organization, like I said, from both the logical and physical perspective. We Are University is a higher education company that deals with preparing students for their future careers. The university is quite large and houses a very high-end network, has very sophisticated technologies that they use. They utilize many different applications that both students and faculty and staff use on a regular basis. And this causes a need for good IT infrastructure and good IT support to support those applications and hardware. Some of the technologies and applications that are currently being used is their ERP system, Mygate, Student Learning Center, Blackboard, and their email, which is hosted by Google. For the logical design, basically the INT building hosts the main backbone of the network. All traffic gets routed through this main backbone. In the INT building, there are a few switches that connect to this main backbone that allows all end users, workstations, and lab machines to connect to the university's network. There is a server VLAN, there's a OSHA VLAN, there's a TSM VLAN, and then there is a general end user VLAN, which is used for faculty and end users. On the graph here, you can see that there are the four logical areas that connect to the overall 6509 Cisco chassis, which routes traffic through a single point through a firewall, and then that goes out to the perimeter firewall and out to the internet. The main backbone on the INT building connects to three other backbones, which is responsible for the majority of the routing that exists on the university's network. Each section of the university has its own backbone, which multiple switches from different departments and buildings connect to these single backbones, which then route traffic through to each other. For the physical layout, my project has an emphasis on the INT building, the Industrial and Technology building. The INT building has 2 floors, and there are a few main locations located in the INT building. The main closet, room 111, hosts all the servers and the main networking equipment, including the perimeter firewall, the perimeter router, and the main backbone. The TSM, the OSHA, and the ITV closets are just main wiring closets that house the switches, in which all the end user devices and workstations that they connect to those. And TSM closets located on room 225, OSHA closet in room 157M, and the ITV closet, which is in room 210. For the physical layout, there are both WAN and LAN links that exist in the INT building. The main ISP link, which connects to our primary internet service provider, is a 1 gigabit fiber network. Um, the university also has a redundant ISP link in case the primary link goes down, and this is a 100 meg fast Ethernet connection that goes through AT&T. The four backbones, the one in the INT building, one in a general services building, one at the residential colleges, and one at Faculty Hall. Those are all connected with redundant 1 gigabit fiber connections. The routing protocol that is used for the backbone is OSPF. Each backbone has its own area for routing, and the main backbone in the INT building is Area 0. For wireless, this is a location of the wireless access points that exist in each building. Both floors exhibit a pretty similar physical location for the wireless devices. They are Cisco access points, and they use software called BlueSocket, which is a basically management control system for the wireless devices. The devices also run WAP2 Enterprise Wireless Security, which uses a username and a password for authentication. VLANs, there are 4 end-user VLANs and 3 server VLANs. There's a TSM VLAN, an end-users VLAN, an OSHA VLAN, and an ITV VLAN, which corresponds to generally certain areas of the building. The building on both floors is pretty symmetric. Both floors exhibit the same type of structure as far as rooms, and the general boundaries that exist on this graph show, on this map show, kind of the general areas of what rooms are covered under which VLAN. The physical links that exist between the wiring closets that connect all of the main routing equipment and switches in the INT building. From the main backbone to the OSHA closet is a 1 gigabit fiber connection. To the ITV is a 1 gigabit copper. The reason that it's using copper is because the location of the wiring closet is close enough that copper was a usable medium. And the TSM closet is also a 1 gigabit fiber connection. For traffic sources, this is getting to traffic analysis that currently exists and goes on the network. We have a couple user communities in the INT building. We have faculty, we have information system staffs, and we have ITV staff. Each of these communities are different size and geographic location, as well as some of the applications that they use. Many of the user communities, however, do use some of the same applications that are that are widespread and used by just about everybody in the university. Faculty users use MyGate, Blackboard, and RacerMail, which is the email system that the university currently uses. The information system staff use the same applications, but they use the applications for different purposes, which is why I put them into different categories. They use the applications for different purposes. Many of the applications serve a variety of different services to employees and students, and so they use those for different purposes. Some of the data stores that exist in the university, there's a file server. The file server stores network shares for different departments in the university. They also house databases for Banner and MyGate, which are used for confidential and private information that is under FERPA. There's the Seaboard data store, which is basically, it's not located in the INT building. However, the Seaboard data store is used for all financial transactions with student ID cards. There is an AD database which houses group policy management as well as user and computer accounts. And then there's also the IP camera system, which acts as a data store for recorded videos for all the cameras that exist in the university. Traffic flow. The ERP system runs through a web browser which uses HTTPS and is used by all users. Like I said, it's a lot of applications kind of rolled into one interface, which everyone uses. The file server uses SMB protocol for file sharing. And is also used by the majority of users. Just about every department has their own network storage and network share that they use to back up and to load files onto for backup and viewing. Video surveillance. The IP cameras use H.323 protocol and is used by the information system staff. This is part of security, making sure that anything that their physical equipment is properly secured. And there are VoIP phones which run on the network, which are also used by all users and runs voice over IP. Traffic analysis. The graph that is shown here is a one-day traffic analysis. It shows the overall traffic for the university from all sources. This is all the traffic that is going out the perimeter firewall, and we see both inbound and outbound traffic. The green represents inbound traffic, and then the blue line represents the outbound traffic. You can see it has a pretty standard trend. During the nighttime, there are really high bandwidth being used due to the residential college, the students who use and access the same network as the faculty and staff, so that exhibits a pretty high traffic usage and bandwidth usage. As it gets towards 5-6 a.m., you see that it tapers off, and because most people are asleep or not having woken up yet. And then during the day, you see a pretty standard increase in bandwidth usage as more and more people go to work for the university, come into the office and use the internet and the internal network. The peak times run about almost 500 megabit per second, which is pretty good. The max bandwidth for the university is 1 gigabit link. So the university is running at about 47-50% utilization rate, which is really good. This is a little bit of type of applications that use what type of bandwidth. It was captured by the Blue Coat Packet Shaper. The Packet Shaper is kind of a QoS device that helps with the prioritization of traffic. In case of heavy loads, it knows what traffic needs to get through and what traffic can be put on queue during peak times. We see that web traffic is dominant. Web surfing, both from faculty and students, and then gaming is also gaming traffic is also up there, using a good percentage of the bandwidth. And we see other things such as flash media, stream services, SSL encryption traffic, and as well as just default, just any normal traffic. So that concludes phase one of the first of the network analysis. It doesn't include everything in the project due to time's sake, but it does hit some high points, gives you an overall objective about how the network's set up, how is it connected, how do people connect to the network to connect to internal storage devices such as the servers, as well as get out to the internet to access content as well. For my second phase, my implementation is the implementation of a data center firewall through the use of a Cisco FWSM Blade module. The reasoning for this device is just for an emphasis on the layers of security that really need to exist to have a really good security solution. Just having one device usually isn't going to cut it. Not just having just a firewall on a workstation is going to be enough. You need multiple layers of security to make it harder and harder for potential malicious intent or threats to have any effect on you. And so those layers just really help mitigate those threats. To the right, we see the the requirements from both management and network staff as well as users for the security solution. We see that it must be able to support the current network traffic. It's not really helpful to have a firewall that's not able to handle the traffic that's needed. Another requirement is that it must work in a hierarchical network. As you'll see later, the university has a hierarchical network, and the firewall must be able to work in that type of hierarchical structure. Another good requirement that we see more with firewalls is that the users demand that the firewall must appear transparent. Users don't want to have to deal with having to get through and just to access their content. They want easeability. They don't want to have to deal with having to go through a firewall by doing authentication or anything like that. They want it to be transparent. They want it to work, but they don't want to see it, which is a pretty good requirement. Another requirement is that it must only allow application-specific ports allowed to maintain security. This is also really important. The firewall has to be able to have the type of configuration abilities to be able to block the traffic that's bad and allow the traffic that's good. So those are just a couple of requirements. The functional areas represents different types of traffic, users, just different ways that that the university uses the network. And that can be separated also by geographic location, which you see in this graph right here. The first floor houses both faculty and staff, as well as on the second floor. And so they're grouped in different functional areas by geographic location, but they're also grouped together, even though they're apart, into a single functional areas because of what type of users are and what type of applications they use. This is a really important slide. This is the threat analysis. Basically, the threat analysis takes certain scenarios and what could happen, and then kind of gives it how likely is this to happen, and what kind of effect is this going to have on the university. So we kind of have a before and after. Before the implementation of the data center firewall, as well as after we implement, what kind of changes are we going to see? Are we going to have enough changes to really justify the purchase and implementation that will be needed to install this firewall? As you can see on the two graphs, one of the things that doesn't really change is the effect. There's not really a lot of letter changes as far as grade of, if something does happen, what is the effect going to be? The firewall is a method of mitigation, a way of preventing the bad traffic from coming in the first place. So if it happens to get past the firewall doesn't really have a way to reduce the effects of what happened because it was already able to get through. But you do see a significant improvement in the likelihood of many things happening. Anything server related generally got a better grade after talking with network administrators. They see that by only allowing certain information and only allowing the traffic that must go through in order to maintain business and maintain users to be able to do their work, by blocking out all that other traffic, you're preventing a lot of threats that could happen, a lot of vulnerable ports that could exist on certain services and applications that may be running on a server that aren't being used are no longer a threat anymore. So those type of things are not going to be as likely to happen, if not impossible to happen. The security levels represent, the levels, kind of the levels of security that are needed for specific scenarios, and this kind of plays into, what kind of security solutions do we need for each security level. As you can see, the first level is kind of the general security level, and this is just normal network security. Overall IDS and IPS over the network links, and firewall, like a perimeter firewall, and that kind of protects. It's a layer of security for the entire network. As we get closer to certain sections of the network, you see in security level 2, we have end user networks. These end user networks have a little bit more layered security, such as workstation firewalls, workstation antivirus, group policy management, switch port security. So it's just adding more layers to the specific parts of the network to make them more secure. Level 3 is the external network. That includes like the perimeter firewall. Those extra things that are designated to prevent bad things and malicious intent from coming into the network. And the most important layer, which deals with my second phase implementation, is the data center firewall, which exists on level 4. Level 4, it contains all the layers of the previous levels, as well as the implementation of that data center firewall. The data center firewall exists as a bridge between the main backbone and the servers. Any traffic that goes to and from the servers must go through the data center firewall, and we'll see that a little bit more later. A little bit about network management. Monitoring is extremely important, especially from a security perspective. A security manager needs to be aware of the status of services, links, server monitoring. All those things need to be properly monitored in the event that something might go wrong. As you can see here, what I have on this graph is the backbone. The 4 backbones. The top left is the main INT backbone, which is the main backbone for the university, as well as the 3 other backbones. Even though they are redundant links, it's important to have monitoring on those links because all the traffic routes through those backbones, and if something goes wrong, if a link gets cut or anything like that, proper monitoring will inform the network management, that there is a problem and that it can be fixed. As also monitoring of the servers, monitoring server traffic as well as server status, network traffic that's generated to and from the server must be properly monitored. It helps recognize any ambiguities that might exist, such as random spikes of internet traffic or extremely long amounts of high bandwidth that is being used, or maybe certain times where there's more traffic than there should be. Monitoring helps recognize those issues, which could be potential attacks, denial of service attacks, maybe data upload, stealing confidential and financial data from the servers. And the monitoring helps to prevent those things. So like I said, it's important to recognize any issues, and you can do that through monitoring. With the new logical design, it's a little different. There's not much change from the previous logical design. We just see that all the servers currently connect to the data center firewall and then route through the main backbone. And also, not only does server traffic going to and from the servers go through the data firewall, but also any server-to-server communication also goes through the router, back through the firewall, and back to the servers. For the implementation of the data center firewall, we have a couple steps. The first step is research. Research is really important. You have to be able to take your requirements that you need, both technical and business requirements, and research firewalls and research solutions, that best fit those requirements. Once you feel like you have that, you then goes on to the next phase, which is analysis. You have to make sure that the firewalls have proper technical specifications, proper configuration abilities. It's able to support certain firewall configurations and benefits, and those have to be part that also coincide with the business and technical objectives. Once then, you get a list of kind of ones that fit your requirements. You have to choose and purchase. Purchasing firewall can be based on numerous factors, price, throughput, just any technical specifications that best fit with the overall objectives. Once the firewall has been purchased, it goes into the testing phase. Testing phase is really important. With firewalls, many things can go wrong, and you can even denial of service yourself with wrong configurations or just lack of knowledge and just early implementation. So testing is extremely important in making sure that what you have is what you need and making sure that it works properly and that the configurations are correct. Once testing has been completed, it goes into implementation. The implementation just starts with just the installation and initial configuration of the data center firewall, which takes a couple steps. The steps involve installing physically the blade that goes into the 6509E chassis, and then also the blade supervisor must also be configured to use the firewall. The blade supervisor is kind of the overhead management for all the blades and all the devices that connect to the Cisco chassis. So that must be configured to allow the firewall. And then next is the ongoing maintenance and configuration. Basically, the configuration and ongoing maintenance is an extremely long duration. The reasoning for this is because there are a lot of services and applications, and there's a lot of servers that exist on the network, and to get those all understood and understanding what traffic is allowed and what traffic shouldn't be allowed for all of the network devices and all the traffic, it will take some time. For the migration and testing phase, the migration will be the installation of the blade module, which is the firewall. There is an easy fallback for this migration, for this installation, which just basically just turning off the firewall or uninstalling the firewall. So in case of the event of anything catastrophically going wrong, it's really easy to fall back to your previous configuration. Like I said earlier, the blade supervisor must be properly configured to use and recognize the FWSM Cisco Firewall blade module. In a way to prevent user impact, we're doing a server-by-server implementation phase, which is why it's such a long duration. And basically this implementation phase is when you go server-by-server, you pick one server, and you say what all traffic needs to go to and from the server. And then you figure that out, you write your rules, and then you go to the next server, and then you do the next server, and you continue until you have all the servers and you figure out all the things that need to be allowed, and then you slowly add those rules in one by one. And this prevents user impact because if anything goes wrong, it's really quick to revert back to the previous state and to make sure that everything's running smoothly. And then it's really easy to pinpoint any issues, because if you implement one server configuration rule and something goes wrong, there's something wrong with that. You can revert, fix that issue, and then there's just not a lot of downtime. The server-by-server implementation is extremely useful because not everybody knows the services and applications and the ports and the information that's going to and from the servers. So gathering the information from system administrators does take some time because they might have to contact vendors to see what ports, what what data is actually going to and from these services and applications on these servers. For the test plan, I said earlier, the testing is extremely important. For the test environment for the firewall, we're emulating a server room with multiple VLANs, which represent the server VLANs that exist. Physical setup of a basic network with the Cisco chassis. Software setup includes the configuration of the blade supervisor, making sure that it's able to recognize and use the firewall. And then also the firewall configuration. This revolves around testing, certain types of configurations of the firewall to make sure that it's usable and that all the functions work. Some of the tools that are used for the test plan include a packet analyzer and a firewall log. The firewall logs and the packet analyzer help the network administrators kind of like diagnose any issues, and it allows us to see what kind of traffic is getting through and what kind of traffic isn't going through, to help us decide whether or not the testing is working or it's not working. These are some of the milestones, basically kind of requirements that the firewall should be able to do during the testing phase. First one is after the installation and configuration of the blade supervisor and the firewall, the routers should be able to route traffic as normal. What this means is that the firewall is sitting at permit all, which basically means that the firewall isn't really doing anything, it's just allowing all traffic. And when we implement that, then it should allow all traffic. There should be no changes, there should be no routing issues, which goes to the second point. Third point, the firewall should block all traffic. We've configured as deny any, basically just to see if the function works on the firewall. And then the next couple options get a little more specific. The firewall should be able to permit certain traffic with permit traffic rule and deny any. Basically, this means that this is only allowing a certain set of traffic information allowed to and from the firewall. So we have to make sure that the firewall understands that it to only allow this traffic and then to get rid of and drop all the rest. And the same for vice versa for milestone 5 is that same thing. You should be able to allow any traffic and then just prevent this one set of traffic from coming through the firewall. Firewall should work at layer 2 transparent mode. There's 2 modes for the firewall: transparent mode and routing mode. And the firewall should be able to operate at layer 2, which just makes it a bridge. It doesn't have a real IP address, and that traffic just goes through it. That there's no routing decisions that the firewall is doing. Firewall should not allow any traffic, not only between the server and user, but between server VLANs as well. This just means that the firewall should be able to recognize and make it to where any traffic that goes between server to server VLANs also runs through the firewall. And then firewall should be able to permit and deny traffic based on VLAN information. What this means is that in the testing phase, there were 4 VLANs, 3 server VLANs, 1 end user VLAN. The firewall should be able to, based on its configuration, differentiate the different VLANs and then permit and deny traffic based on those VLAN rules.